Welcome back to Physics 151 Online. We're making a change right now and turning our attention from problems where we consider the motion of objects in relation to forces that act on them, and we use Newton's laws to do that, to a section of the course where we're going to define some new terms and show an alternate approach to solving motion problems by understanding what we mean by the terms work and energy. Work is used often in a colloquial sense to mean a variety of different things, but in physics there's a very specific meaning to the quantity, and so we have to understand the definition and then be able to apply it and calculate it in specific situations. If we imagine the simple case of a constant force that's acting on an object that moves just in a single direction, we can write down a general expression for the amount of work that that force does. And to make this a little bit more general, let's imagine that although the force is a constant force, it's inclined at an angle theta from the direction of motion. So here we see a block moving along the x-axis, and we'd like to know, as that block moves through a displacement delta x, how much work does that force do on it? Whoops. And so the definition for work done for this situation is that the work is equal to the component of the force along the direction of motion, if this horizontal direction is the x-axis, times the displacement. And so realize that this component can be either positive or negative depending on whether the force is aligned parallel to, or has a component parallel to, or opposite to the displacement. And so f sub x, the component of f along the x direction, would be given using the right triangle here that we could make with the force as the hypotenuse. It would be given by f times the cosine of the angle theta times the displacement delta x. If theta is equal to 0, then we simply get f times delta x. Now the units for work, since the work is defined as a force times a displacement, are Newton meters, and we give a special name for this. We call this the joule, in honor of James Prescott Joule, who really in the middle of the 19th century was the father of the subject that we now call thermodynamics. And through a series of very clever experiments, Joule was able to establish that work and thermal energy were very, very closely related to one another. Now, what about situations where either the force is not constant, it changes as the object moves, or maybe where the object is not moving in a single direction, but it might be moving along a path that has components of x, y, and z? What about those situations? So let's generalize our definition. First, let's consider a non-constant force. So if we plot the component of the force acting along the x direction versus the x position of the object, we might have a curve like this. The yellow line shows a changing force, and so let's figure out how we can calculate the work done by that force between the initial position x1 and the final position x2. And you'll note that if the force were constant, then the work done would simply be the value of the force times the displacement. But since the force is changing, we have to figure out a way to add up the areas of these tiny little rectangles. You'll see one here indicated in red, and we're going to use our knowledge of calculus to imagine that the width of that rectangle is a very, very tiny element, an infinitesimal displacement dx. And so then the area of that rectangle would approximately be whatever value the force had at that point multiplied by the width of the rectangle. So the differential amount of work done during that very tiny displacement would simply be the value of the force along the x direction times that displacement. So adding up all of those pieces would give us the net work. So the total work would be, using the language of integral calculus, it would be the integral of f sub x dx from x equals x1 to x equals x2. And we imagine that this f sub x might have, as the diagram indicates, some dependence on the x coordinate. And we'll show some examples of these kinds of forces as we move through this section. Now, that still applies only to an object that's moving in a single direction, only along the x-axis. What about an object now that might be moving along a general path? So how are we going to define the work? And we use a mathematical definition called the dot product between two vectors in order to make this definition. Imagine now the simpler case of a constant force. All right, so now go back to just thinking about a constant force, and that there is a displacement, delta S, that takes the object from its initial to its final point. But it's not just along the x-axis. It might have components along x, y, and z. The dot product, F dot delta S, is the work done by that force. Now, of course, that's just a mathematical symbolic notation. So what does it mean? Well, the way that we'll explain what it means in just a second. Let me just move on to the non-constant case, and then we'll show examples of using both of these equations. So now if the force were not constant, then what we would have to do is take our displacement vector and replace it with a tiny differential displacement, taking us between two very, very nearby points in space, and form this same dot product of the force vector with that, but then integrate the quantity between the initial and the final positions for the object. So of course, in order to evaluate these expressions, we have to know what we mean by the dot product. So here's how it works. Some sources will call this the scalar product of two vectors, but usually we refer to this as the dot product. What it means geometrically is it's telling us the component of the first vector f lying along the direction of the second vector multiplied by the magnitude of the second vector. So the dot product is a measure of the degree to which two vectors lie along the same direction. We'll see in just a minute that the dot product of two vectors is a maximum value if they are parallel to each other. It's equal to 0 if they're perpendicular, and it's equal to a minimum value if they are anti-parallel, because in that case the dot product will actually be negative. So for the most general case here of two vectors A and B, we draw them so that their tails are in the same place, and then that defines an angle theta between them. So A and B form the dot product A dot B using this notation up here, this definition. The component of A lying along B is A cosine theta. The magnitude of B is B, so that AB cosine theta is the dot product of vectors A and B. Notice, again, that the result is not a vector. The result is just a scalar number. And so that's why this is sometimes called the scalar product of two vectors. All right, in component notation, if we want to deal a little bit more easily with a situation where we may not know the angle between the two vectors, but we may know their components. For example, A is equal to AXI hat plus AYJ hat plus AZK hat. Using unit vector notation, you can show that A dot B for that general case is simply the product of the similar components of the two vectors then added together. So it's AXBX plus AYBY plus AZBZ. And so with that in mind, now we can do two simple examples that show how to handle situations where we've got a force acting on an object that's moving from one point to another. So we'll do a numerical example here, assuming that the force numbers 5 and 6 are in newtons, and that the values for the positions S1 and S2 are in meters. So we're given the initial and the final position, and we're told that while the particle is undergoing this displacement, that the force acting on it is given by 5I plus 6J. So first of all, to form the dot product, F dot delta S, we have to calculate delta S. So the displacement vector is the final minus the initial position. Right? If we do that with these two vectors, we're going to get 5 minus 3I, and then 8 minus negative 2J. So this becomes 2I hat plus 10J hat. Now we're ready to take the dot product between the vector F and the vector delta S. And that's pretty easy, remembering that that dot product will simply be the product of the similar components added together. So it'll be 5 times 2 plus 6 times 10, or 70 joules. All right, because remember, force in newtons times displacement in meters gives us newton meters or joules. Really simple example. So that's the work done by this constant force F as the object moves between some initial and final location. Now, a not so simple example is given by the case where one of the components of the force is actually changing with position. And there are real situations where this might actually happen. So just for now, let's consider the abstract case without wondering about without worrying about where it comes from. But let's simply work out the integral that we need to evaluate. So the integral is given by f dot ds integrated from S1 to S2. So first, let's write down what that infinitesimal displacement vector is. ds, as an infinitesimal, has an infinitesimal displacement along I hat and then along j hat. I'm not given a k hat component for these two vectors, and so there isn't any net motion along the k direction. But if there were, then we would add a dz times k hat to this infinitesimal displacement vector. But here we have a situation that's just a two-dimensional situation. So now, f dot ds, we carry that out the same way we would any normal dot product. We take the x component of f, which is 5x, times the x component of ds, which is dx, and so that becomes 5x dx. And then we do the same thing for the y components, 6 and dy. So 5x dx plus 6 dy, and this quantity has to be integrated between the initial position, S1, and the final position, S2. How do we do that? Well, what we have to realize, looking at the integrand here, is that there's a term dx and there's a term dy. So we integrate the sum, and just as in examples that you're familiar with, the integral of a sum is the sum of the two integrals. So we integrate the first piece, 5x dx, and there's no change in y along this direction, and it doesn't depend on the value of y. And so the variable x is only changing from 3 to 5, right? 3 is the initial x coordinate, 5 is the final one. And so we'll form that integral, and then we'll add to it the integral that we get for 6 dy as y changes from -2 to 8. All right, so what do we get here? The first term, just go back to that for a minute, 5x dx, well, that's the same as x to the first, and so we know the integral of x is x squared over 2. Right, so that will give us 5x squared over 2 evaluated between x equals 3 and 5. And then I'll go back for a second. The second integral, 6 dy, well, 6 is just a constant, so when we integrate that, we simply get 6y evaluated between y equals -2 and 8, right here. So the first term, what are we going to get? Well, x squared, 5 squared is 25, right? So that's 125 over 2 minus what we get with 45 over 2. 125 minus 45 over 2 is 80 over 2, which is 40. Right? 40 comes from just this term. And then the second term, well, 6y, when y goes from -2 to 8, is going to give us 60. And so we get a net result of 100 joules. So it may not seem obvious why we might want to do that, but there are many forces in nature that depend on position. And so one that we'll see some examples in this part of the course will be that of a spring. As a spring is compressed, the force that it exerts depends on how much it's compressed. And the same thing holds true if it's stretched. So that will be one area where we will use these equations in the course. I hope this is a useful introduction to work, and I will see you in class.